If you're watching this video, this is part 2 for Physics 100 Fluids Lab. I haven't yet succumbed to the coronavirus. Keep your fingers crossed. All right, Archimedes said that an object partially or completely submerged in the fluid feels an upward buoyant force B that is equal to the weight of the displaced fluid. In part 1, we completely submerged the aluminum solid in the water, and we figured out the weight of the displaced fluid by using the scale, and we compared it by the apparent buoyant force between what it weighed outside the fluid compared to what it weighed completely underneath the fluid, and we wanted to verify that Archimedes was right within a few percent of experimental error. Hopefully you succeeded. In part 2, we're going to repeat the procedure, at least I am. We're going to dunk it not under the water, but under 2 new fluids. The first one is salt water, which is denser than regular water, so the specific density is greater than 1. The second alternative fluid that we're going to completely submerge the aluminum solid is ethyl alcohol, whose specific density is less than 1. Now, the formula for the buoyant force is the weight of the displaced fluid. It's the mass of the fluid times g. But mass, we learned, is density times volume. So the mass is the density of the fluid times the volume submerged times g. If we compare the buoyant force under the new fluids, salt water and alcohol, with the original fluid, regular water in part 1, we can get the ratio if we calculate it. And the only thing that changes physically when you dunk it under salt water versus regular water is the density of the fluid. You are not changing the acceleration of gravity, g. You are not changing the volume submerged. So if you dunk it under a denser fluid like salt water, you should get a larger buoyant force. From this equation, you can see that the volume submerged terms and the g's cancel. So the density of the fluid over the density of the water is the specific density of the fluid, but that's the ratio of the new buoyant force under a different fluid compared to the old buoyant force in part 1 under water. Bottom line, we determine the buoyant force by weighing it completely underneath salt water and ethyl alcohol. And we compare that buoyant force from part 1 completely submerged under the water, and we get the specific density of the high density salt water and the low density alcohol. Won't that be fun? Let's go. Talking a little fast, but who cares? All right. So this technique is really easy. We don't have any water to collect in an overflow catch bucket. All we do is attach this thing and carefully drop it into the tube. This blue thing is salt water so you can see it, and it's more dense. All you got to do is make sure the cylinder does not touch the sides of the plastic container, because we don't want any frictional forces. All we want is the weight force and the buoyant force of the fluid. Then we tie it off. This takes years of practice. And we counterbalance to find the new weight. It's going to weigh less than it did under the water because we get a heavier, denser liquid. And so we counterbalance it, and boom, and we read it. I'm going to repeat it, which I'm not going to show you. We just dunk it under the alcohol. Alcohol is less dense, and so it's going to take more weight to counterbalance because we're displacing a lower mass density fluid, so the buoyant force is less, so the submerged weight is greater than water. Take the data, and we're ready to rock. So let's take one quick look at the data table. I'll talk a little slower this time, maybe. Not used to making videos. There's some gentlemen following me around. Watch this guy. So in part 1, when you weighed it in the air outside the water, this is what we got. We also weighed it completely submerged under the water. The difference between these two, we figured out, is the true buoyant force. And hopefully that was close to the weight of this displaced fluid. Now, we go on into part 2. We copy over, we know what it weighs in the aluminum. We know what it weighs submerged. When I put it under the salt water, which is denser, notice how it weighs less under salt water than fresh water. When I submerge it under low density ethyl alcohol, notice how it weighs more than it did submerged in water. Based upon that, we can figure out the buoyant forces of those two. And then once we have the buoyant forces, we can go on and apply what I showed you here, that the buoyant force of the liquid divided by the buoyant force of water is a specific density. We just import the data. So for salt water, this buoyant force in the salt water should be greater than regular water. So the density, specifically speaking, is greater than 1. And for the ethyl alcohol, we calculate it, it will be less than 1. And you can answer this question. I'm done. Cut the video. Thank you.